All right, everyone. In the previous lectures, we learned how to find the electric field for a point charge or even group of point charges, such that they have, finite distance between them. And even if they're, let's say, multiple point charges, and I'm mainly talking about source charges, two, three, four, five, as long as they have some distance between them and you're looking at the electric field nearby, using the superposition principle, we could find the electric field. Here we're going to talk about then continuous charge distribution, basically electric field for the continuous charge distribution. And we're going to try to then find electric field for this type of distribution configuration, looking at using the Coulomb's law and the Gauss's law, and see the difference between those two ways of solving for the electric field. All right, so again, let's talk about in terms of what I mean by that, and including like what I mean by continuous distribution. So if you have a point charge, we talked about a single point charge can give you electric field at some distance r from the point charge. And that's because this point charge acts like a source of electric field in this region. And even if you have several point charges, right, so you can find the electric field using the superposition principle. But then at some point, you can have a really large number of point charges, and also they're very close to one another. So basically, think like this: when the distance between charges in a group of charges may be much smaller than the distance between the group and a point of interest, that means, let's say we have a lot of charges like this, and the distance between them is much smaller than, let's say, this point of interest, then we can talk about that this is now a system of charges, and we can model it as a continuous charge distribution. That means, this could be sort of like a maybe like an object or a rod where we have all of those charges inside, and now we have contribution from all of them at that point P. So basically, that becomes like a continuous distribution. So the system of closely spaced charges is equivalent to a total charge that is continuously distributed along the, some line that becomes basically sort of like a rod that I was mentioning. So it could be like one dimensional, or could be a surface, could be two-dimensional, right? Or it could be, let's say, some kind of, volume, or, that means over three-dimensional, sort of like, let's say, a system or an object. That means we are not dealing with a point particle or collection of point particle. We're dealing with, system of continuous distribution. All right. So for example, let's look at this to be some kind of object. Okay. Again, it's some kind of general shape, but let's say that this is could be an object, or maybe a region where charges are again very, very closely spaced, and some point of interest. Now, one thing we have here is that electric field at that point, let's say point P, right, will be then due to each individual charge in this object or in this region. But if you're trying to then find the electric field, as we learned, right, in the previous lectures, if I want to find the electric field at that point P, I need to, add them all together. So find the net electric field. It's relatively straightforward if you have two, three, four, five, I don't know, even 10, let's say, you know, um, point charges, source charges. But obviously, it's going to be very tedious and difficult if you have, hundreds or thousands or billions of point charges in that region. So then what we do here is we take the region, break it down into small elements. So let's say I'm looking at just this small element, which is part of this system or part of that region, right, or the object. And I'm going to say that this small element has charge delta Q, where let's say the Q is then the total charge of the system. Then this delta Q1 is the charge of that small element 1. There could be another smaller element that I can look at, delta Q2, in terms of its charge. And then what I have here is this, at point P, then you can see, right, delta Q1, which is a distance R1 from that point P, contributes in terms of this electric field E1. or delta E1. That means think like this. First of all, I'm saying is that total charge Q is delta Q1 element plus delta Q2 element plus that, right? All the way to some delta Qn, n number of elements. That means, or maybe let me put it like I number of elements. That means I have really large number of elements here in the system. And the total charge is sum of all the charges of those tiny elements. Then when I'm looking at then the electric field, then you can see, right, each small element, contributes to that point P, right, with its, because it has a charge and it has some finite distance from that point. So the electric field, delta E1 due to the small element. Then delta E2 is due to the second, small element. Delta E3 is due to the third small element, and so on and so forth. That means to evaluate the electric field of a continuous charge distribution, we again, so divide the charge distribution into small elements. Each contains delta Q charge. Calculate the electric field due to one of this element at point P. That means what I can do here is I can say that I'm going to take this delta Q1 and I'm going to find its contribution. So what is then this delta E1? By, how much this element contributes. That means I need to find the electric field expression for this element 1. Then I can generalize it. I can say then what I'm going to do, I'm going to just, do the same thing for element 2, same thing for element 3, same thing for element 4, 5, all the way to ith number of elements, and then basically add them together. That means then evaluate the total field by summing the contributions of all the charge elements. Okay, so obviously you can see how tedious it can be if you have a large number of elements, but still each individual element's delta E sub I, right, is same, equation that we had learned previously, which is K times the charge, right, which is in this case delta Q, divided by its distance, R sub I square, and times the unit vector, which is, remember we said the point charge, electric field due to some point charge is K Q over R square R hat. That was the equation for the electric field. I'm just saying that right now I'm just looking at this element which has a charge delta Q instead of just Q. Okay. But then remember I have a large number of those charges together in a small region. So I need to then add them all together. That means electric field is delta E1 plus delta E2, delta E3, right? All of those, contributions combined together. Okay, so because the charge distribution is continuous, then I need to find the sum. Okay, so sum, you can say, right, of all the, let's say, delta E1 plus delta E2 plus that, right, plus delta EI. That means all of them added together. Well, if you have a really large number of elements, right, and you have a continuous distribution, so we know, remember, hopefully from calculus, that this then basically, when we take the delta, the limit, well, delta Q sub I approaches 0, then this sum pretty much becomes an integral. That means what we need to do here is to find the electric field, the net electric field at that point P, right? We need to then integrate, where integral becomes Ke, then integral of dq over R square R hat. That means this is the equation for the electric field for the continuous distribution. So I can say that in order for me to find the electric field for that continuous distribution, or that system that I had, for example, um, what I mean by this, right? In order for me to find the total electric field due to this system of, a continuous system of charges, I need to then integrate. Okay, I need to use this integral. All right, so K integral dq over R square R hat. All right, so the previous slide also, talked about in terms of how we can have this distribution along some line or some surface or some volume. That means one thing we can see here is we can have basically either distribution over some volume. So let's say maybe I have a sphere. Sphere is like a three-dimensional object, and all those, you know, all the charges, right, that I have, that means, those delta Qs, right, distributed throughout the volume of the sphere. Okay. Where the Q here is the charge of the sphere, and then V here is the volume. So this is the charge, and this is the volume. And one thing I can define here is the volume charge density. So that's when a charge is distributed evenly throughout the volume. So volume charge density is given as a ratio of charge per volume. Remember the density, right? Density generally we talked about, in previous, let's say, mechanics class, where the density would, for a linear mass density, right? So mass density was mass over volume. That means if you want to find mass density, you do mass over volume. You want to find, volume charge density, then you do charge over volume. That means how the charge is distributed over the volume. Okay. So we have rho, which is technically we use a lot in physics. So in this particular, chapter, the rho is going to be in terms of the volume charge density. It has units of Coulomb per cubic meters. So rho equals Q over V. Then we can, in a way, if I'm choosing the small element, right, the tiny element, then I can also look at in terms of what is that, in terms of, like, let's say, small element that has a charge dq, delta q then becomes sort of like a dq. And it also has a size where now I'm looking at the volume of that small element, which is different from the total volume. So this becomes dv, right? Then this ratio technically is also equals to dq over dv, where dq is the charge of my small element, dv is the size of my small element, like, three-dimensional size, right? Volume, because of the volume of my small element. So then one thing you can see that the rho is equal to dq dv. Also, it's q over v. So if I rearrange, then I can see that dq then equals to rho times dv. Okay. So this is how we can remember that equation for the electric field, where integral, um, for the, so let's say, continuous distribution, right? So k dq over r square r hat. Now, if you're dealing with a volume charge density, three-dimensional object or three-dimensional system, then this dq can be replaced with rho dv. Okay, that means we can say that, um, let's say the electric field is equals to integral of k, then rho dv over r square r hat. Okay. And then here we're going to go like from, volume one, volume two, and things like that. That means we can change dq into, let's say, into volume. Okay. And if it's into volume, so then technically one of the things I can say here is that maybe this is integral of, let's say k rho, then dv can become like dx, dy, dz over, and then r depends on, my particular configuration. So let me keep it for now, just r square. Then in a way you can see, right, this becomes basically the uh, three triple integral, right? Integral of x, integral of y, integral of z, and then k constant can come out, and then the rho also technically constant, but then you can do then dx, dy, dz, and if let's say r squared can be also x squared plus y squared plus z squared. All right, so I'm just giving you, like, let's say, in terms of what it can be. All right, so yes, it is a triple integral, but then each integral is just basically just nothing but a line integral, right? So dx is just integral dx, integral of x, right? So the second integral you can just separate it in terms of just another one-dimensional integral. So you can break it down into a single one dimensional integrals. But this is what we have, and we're going to be using this, but in a much simpler way than, let's say, you might do in calculus. So I'm going to show you that, let's say, even if we have a volume integral, for us, it's going to be, straightforward enough that, for example, whenever we go and use a volume integral, we're usually going to be then using Gauss's law, which really simplifies our integral calculations using the symmetry. All right, so let's say this is kind of what we have. Get rid of this, because then another thing we can have here is we can have then a surface charge density when a charge is distributed evenly over some kind of surface area. That means, for example, maybe I have like a sheet like this where charges kind of distribute like that. And let's say I want to find the electric field some point P over here. Then I take this and find then there's some kind of element that has a area dA, right, and has a charge dQ. And then let's say Q is the total charge, A is the total area. Then what I can do here is I can look at how the charge distribute over the area, and this ratio is, which we call surface charge density, is given by sigma. So sigma is charge per unit area. This is for the total thing, but this is also equivalent to if I'm looking at dq over dA. That means, this is also applied to that small element. All right, so again, hopefully you guys can see, let's say, why I can use this ratio and say that this is equals to rho, and also this ratio is also equals to rho. Let's say the same way I can, let's say, use the Q over A ratio, which is equals to sigma, and dQ over dA also equals to sigma. So think like this. This is kind of equivalent to saying if I have, I don't know, let's say this piece of gold, for example, and if I find the mass of this gold and the volume of this gold, and if I find the density of this gold, this will be just mass over volume, right? Mass over volume of this piece of gold should give me the density of the gold. Now, what if I just take small piece of this gold, take out small piece, and find, let's say, its mass, let's call this dm, and find its volume, dv, right? Well, if I do the ratio of that small mass divided by small volume, shouldn't I get the same density? Because density of gold doesn't matter if I'm using a big piece, small piece, tiny one, right? Doesn't matter the shape or size. As long as I have the mass and the volume, I should get the same exact density for the gold. Same thing is here. That means this surface charge density is equal to the same ratio of the total charge over total area, or element charge over element area. Okay, that means taking this rearranging, you can see, right, then dq is equals to sigma dA. All right, again, that means, if this is electric field due to some kind of, two-dimensional distribution, so I can say that then this is k times sigma dA over r square r hat. So this technically can be changed into that. Same way, then last one, I have a linear charge density, which is just when a charge is distributed along a line. So basically, this is like a one-dimensional. So maybe like a line where there are charges distributed like this. And if I want to find electric field some point P, then I need to then understand that if the Q is the total charge, and let's say L is the total length of this distribution, right? Then charge over length is defined as linear charge density. So we're given with Greek lambda. All right, so this lambda is not a wavelength lambda. You use lambda sometimes in physics for wavelength, but this is linear charge density. So by the way, sigma has units of coulomb per square meters, and lambda is coulomb per meters. You can see, right? Lambda is one-dimensional, sigma is two-dimensional, and rho is three-dimensional distributions, right? They represent each one, sort of like a different degree of freedom. So lambda equals Q over L, and that means it also equals to dq over dl. That means if I look at just a small element here as a charge dq size dl, then I can look at in terms of its contribution compared to, instead of like the entire thing, and then dq equals lambda dl. That means, again, if I go back and look at this, electric field integral, then this can be k lambda dl over r square. So then again, a lot of times, this will allow me to then do an integral over length instead of like, let's say, dq. So those are in terms of those densities, linear charge density, surface charge density, and volume charge density. And a lot of times when we're doing the problem like this for electric field, for a continuous distribution, we we use this, charge density value, like let's say constants. All right. So now, in terms of when should we use just a general equation of electric field, when should we use this, electric field, for that one that we just learned in terms of charge density, linear density. That means, like let's say the next few slides kind of give you a little of like strategy. So establish a mental representation of the problem. Think carefully about the individual charges or the charge distribution and imagine what type of electric field it would create. Appeal to any symmetry in the arrangement of charges to help you visualize the electric field. Basically, the idea is that think of it like this. Are you given, let's say, small group of charges where you can just use the simple superposition principle and add them together, or are you given continuous distribution of charges? Okay, so it means are you analyzing a group of individual charges or continuous charge distribution? And the answer to this question tells you how to proceed in the analyze step here. If you're analyzing a group of individual charges, use the superposition principle. That means if you have just a small group like 2, 3, 4 charges, and the distance between them is kind of comparable to the distance or to point P, then you're using basically just a superposition principle. Superposition principle means that net electric field equals electric field 1 plus electric field 2 plus, let's say some, small n number of electric field kind of added together. Uh, Obviously, if you're analyzing in continuous charge distribution, replace the vector sums for evaluating the total electric field from individual charges by vector integrals. That means we have to then do the integration. So the charge distribution is divided into infinitesimal small pieces, and the vector sum is carried out by integrating over the entire charge distribution. That means E here is equal to an integral of k dq over r square r hat. So then you basically use this equation to integrate, where here you just basically each, um, let's say, each electric field can be just given in terms of, let's say, k q over r square. So if it's electric field 1, it's kq1 over r1 square. Electric field 2 is kq2 over r2 square, and so on and so forth. But then here we just, you know, find the expression for one, let's say element charge, and then integrate over the entire surface, either one-dimensional surface, two or three-dimensional, right? So you basically decide depending on the problem. All right, so, and a lot of times consider the symmetry when dealing with either distribution of point charges or continuous, because a lot of times we can see that X components, for example, can cancel out, or Y components can cancel out, and things like that. So a lot of times we can just use the symmetry and, save ourselves some time by understanding, realizing that some of the components can technically cancel out. So simplify our calculation. All right, so finalize, check to see if your electric field expression is consistent with the mental representation and if it reflects any symmetry that you noted previously. All right, so that means, does it make sense or not? A lot of times, you can figure out if you calculate correctly, if you get the magnitude and direction correct, depending on the configuration you have, and depending on the type of charge you have, right? If your source charge is positive, then you should get, like, let's say, positive number. If your source charge is negative, you should get a negative number, and so on and so forth. All right, so let's look at then an example here. So a rod of length, so there's a length L, has a uniform positive charge per unit length, and that's basically our lambda, and the total charge Q. That means what we're given here is we're given a rod that has a length L, and it has a charge distribution, right? Linear charge distribution of lambda. Okay. And it's pretty much you can say it's a uniform positive charge per unit length. Remember, charge per unit length is lambda. That means it's positive. If the unit, this um, charge um, charge distribution, right? So, or you can say like a charge density, either linear charge density or surface charge density. If they're positive, that means your object itself has a total positive charge. So that's why it says uniform positive charge per unit length. That means this lambda is positive. Lambda is positive, Remember that because Q over L, that means Q is positive. That's why you're dealing with the positive overall distribution. Now, what we have is this. It says asking us to calculate the electric field at the point P that is located along the long axis of the rod and a distance A from one end. That means we take then the point P as at an origin, and then we place the rod such that it has a distance A from the origin. So then that point P has a distance A from one of the ends, which is basically the left end of the rod. And what we want to do here is we want to find electric field at the point P due to this continuous distribution. All right. So one thing we have here is this. Because we were given that it's a uniform positive charge per unit length, that means our lambda was positive, we can assume that any electric field that we have at that point P will be radially away from our distribution, right? Because remember, if the source is positive, electric field is radially away from that. So that's why this electric field is, as a vector, it points to the left, radially away from the charge. Something like that. All right, so then we obviously identify that this is a continuous charge distribution where lambda equals Q over L, and it also equals then dq over dl, because one thing we're going to do here, we're going to choose a small element. So we're going to choose this small element over there. And remember, the idea here is to choose a small element, find the expression of the electric field for that element, and then generalize and integrate over the entire thing. That means I'm going to say is this small element going to give me some kind of dE at that point P. dE is the electric field that small element, let's say, generates. Now, this equation becomes basically K dq over R square R hat. Okay. Now, what I have here is then this. I can see that my small element has a distance x from that point P because it's on a horizontal axis. So in a way, I can say my R here is equals to x. R is equals to x. And I can see that my electric field is pointing to the left. So then R hat is equals to negative I hat. All right. So also, I can see that dq is equals to then lambda dl. That means, sorry, well, lambda dl, but since it's horizontal, I can say it's lambda dx. That means I can say lambda is dq over dx, and dx is the size of my small element. That means rearranging this becomes dE is equals to, so k, then dq is replaced with lambda dx, then r hat is with negative I hat, and then r square is basically x square. This is my expression for, dE. And again, dE is just basically the tiny element contribution at that point P. All right, so then what I do here is I just basically integrate both sides. The left side is just basically E. Let me for now just, ignore this I hat for a second. We just put it here. We know that, that's negative I hat. It's there. Let's calculate the magnitude. So then if I integrate left side, it's just E. Then on the right side, then I have an integral of k lambda dx over x squared. Then I want to see, all right, so what do I want to integrate with respect to? Well, I want to integrate from rod from this point here, let's say point 1 to that point 2, which is, the entire rod. And how far away the point 1 is from the point P? Well, point 1 is a distance A from point P. Well, how far away point 2 is from point P? Well, it is distance of L plus A or A plus L, like that, right? Because it's A plus L, that's how far away point 2 is from my point P. Point P is a point of interest. Then I can see that K is a constant, can come out of the integral. Lambda is a constant, can come out of the integral. And then what I have here is then I'm integrating dx over x squared with the limits of A and A plus L. Then this is k lambda. I imagine you should have no problem integrating this. So this is -1 over x. Remember, the idea here is we're doing this, right? So I can just say, okay, this is x minus 2 dx going from a to l, a to, a plus l. And remember, so integrating is x minus 2. If you're integrating this becomes x minus 2 plus 1 over minus 2 plus 1. So this will give us basically negative, right? Minus 2 plus 1 is -1, and x minus 2 plus 1, x to the -1. So -1 over x with a to a plus l limits. All right. That means I can calculate this then to be e is equals to k lambda. Then here I end up with 1 over a. If I rearrange everything, 1 over a minus 1 over l plus a. Then from here, what I do, because I don't want technically my final expression to include lambda, which is the linear charge density. So I can say that the lambda is equals to q over L. So I can then replace this k q over L, 1 over a plus 1 over L plus a. And if I combine everything together, I get k q over a times L plus a. And that's my final answer for this electric field. That means if I have a rod with a uniform charge density, distance a from this point P, and a is, is some finite distance, um, then electric field that it generates will be kq over a L plus a. That means this will be basically my answer. Now, I can also look at something a little bit more specific. For example, what if this rod was much further than, see, over here is actually A is less than L, right? So let's say A is less than L. But what if, let's say, the rod was far away, really far away, such that basically A is much greater than L. Okay, so I'm looking at, maybe like a special condition for that. Now, electric field then for that this rod would generate if it was really far away, where a is again distance of the rod compared, with respect to point P, then you can see, right, if I'm saying that a is much greater than L, then L basically becomes, almost negligible. So I can just ignore it. I can say it's almost zero. So then this equation kq a times L plus a, if L is zero, becomes kq a times a, so it becomes kq over a squared. And you can see, right, kq over r squared is basically the same as kq over r squared, which means that a is the distance of that rod, q is its charge. So really, really, really far away from the point P, it basically acts like a point charge. So it's just kq over r squared, where q, kq over a squared, but a is just a distance. That means really far away, it's going to act like a point charge pretty much. But at the closer distances, right, where let's say a is either comparable or let's say less than L, then this is then the electric field expression. All right. So let's look at another one here. And this one here is a uniform, again, so it's a distribution. So we have basic electric field due to a uniform ring of charge. Okay. So a ring of radius A carries a uniformly distributed positive total charge Q. Calculate the electric field due to the ring at the point P lying at a distance x from its center along the central axis perpendicular to the plane of the ring. That means, well, think like this. So this is my, image, right? So let's say I'm going to make it bigger. So let's say this is the ring. Okay. Like that. And what I have here is I put such that this is the x-axis and this is, let's say, the z-axis. So ring is in the yz plane. Okay. Where what I have here is, let's say this is the origin, and I want to find the electric field at some point P. Okay, so that's kind of like the idea. All right, so again, what we do here is we take, and first of all, like, we try to recognize what type of problem we have. Obviously, this is charges distributed around the ring. That means it's a uniformly distributed positive total charge Q. That means this is continuous distribution. This is being now point of interest. What I have here is I choose some small element right there. So let's say some small element right there, and I can say dq, then its size. Sorry, its charge, right? And then its size here is just dl. Okay, so dq, its charge, dl is its size. Okay. Then I can see that it is this distance r from the point P. So at point P, the electric field, remember, it's radially away. So I draw a radial line. That dashed line is the radial line. And the electric field will be that. It just, the electric field just happened to be some angle theta, which there are same theta both sides, uh, below the x-axis. That means this theta, right? Sorry, this dE can be broken down into dex and dey, which is written as like perpendicular, but this, let's say, dey. Okay. Now, what I have here is then the equation for dex is then de cosine of theta. For dey is de sine of theta, because I'm breaking down into components. Now, one of the things is important to understand, as I mentioned, in the previous slides, right? The symmetry is an important, important to look at if there are ways to simplify a calculation. So one way we can simplify, we can see that if I go, so this is, let's say, point 1 over there. If I go to another point, let's say point 2, which is right below that point 1, I can see that electric field that it generates going to be this guy over here, which, if I break it down into two components, right, x and y component, I can see then I have x and y component for each vector, and see this perpendicular or y component of both of those, point 1 and point 2, going to be the same magnitude but opposite directions. Same magnitude, opposite directions, and that's going to be true for some point 3 over here, another point 4 over there. That means symmetry then, will allow me to, eliminate that perpendicular or y component. Well, that's why you can say, right, it's written as perpendicular because it could be for point 1 and 2 it's dy, point 3 and 4 it's dz, right? So let's say that this is perpendicular component, and then the sum of this perpendicular components, right, gonna end up going to 0. So then we can ignore that. Okay, that means this is gonna end up being equal to 0. That means this, we can see, right, all of the components going to give us contribution in a positive x direction, and those, that means those x components, right, they're never going to cancel out. They're actually going to be, adding up to one another. That means what I have here is I can say that, x component survives, and then I can write it down. So dex equals then de cosine theta. Now, what is my dE? Which is basically the magnitude of the electric field that point 1 will generate. Well, dE is equals to k dq over r squared. That's, we already know. Let's say that means if it's a, a small element, its contribution is k dq over r squared. Now, we learned that one thing I can do here is I can make a, I can replace dq with other things. But for example, here, I'm going to leave dq, but I'm going to say that r, which is the distance from my element to the point P, can also be written, you can see, right? So you basically create a triangle over there. So r is equal to then square root of a squared plus x squared, or because in the equation I have r squared, I can just say that r squared is equals to x squared plus a squared. So that means I have k dq, then r squared becomes x squared plus a squared. So that's my dE. How about cosine of theta? Well, this is my theta. Remember, cosine theta defined as the adjacent over hypotenuse. Well, my adjacent is x, my hypotenuse is then r. So x over r, which means it's x over x squared plus a squared 1/2, right? R is the square root of x squared plus a squared. That means if I come back here, I can say, all right, my dEx equals then dE cosine of theta, where dE is equals to k dq over x squared plus a squared. And then cosine of theta ends up being then x times x squared plus a squared 3/2. If I combine those together, then I get k x dq over x squared plus a squared. Sorry, guys, this one is 1/2. Then here it becomes 3/2 if I combined those two together. All right, so then what I do, I then integrate both sides. On the left side, integral of dEx becomes just ex. And on the right side, then I have the integral of kx dq over x squared plus a squared 3/2. Okay. So that becomes basically my integral. All right, so now let's look at what we can remove from the integral. So I can take out k, I can take out x, I can take out x because as I go around the ring, the x doesn't change, right? So the x value doesn't change for this particular example. That means every element, 1, 2, 3, whatever I count, for all of them, x is exactly the same, okay? So it can be removed. Same with the x squared plus a squared, which is, they all have exactly same distance r. That was not the case for the rod. For the rod, if I would do my first element, then second element, third element, so you know, I have different distance, right, from the point P. Here, all the points have exactly same distance from that point P. They all have the distance r. So I can remove that, which allows me that, to just keep the dq over there. And that means everything can just come out. This is 3/2, right? And the dq just stay there, and I can just integrate for that. And integral of dq is just nothing but q. So integral of dq is then the total charge q. So then this becomes k x q over then x squared plus a squared 3/2. And that's basically my calculation for the electric field at that point x due to this ring. Okay. All right, so this is still assuming that we are dealing with x, which is a distance of that point P, that is kind of, comparable to, radius A for the ring. That means it's either same as the, equivalent to A or just a slightly greater than A. But what if we are looking at this case where x is much greater than A? That means it's really, really far away. Okay. Let's for example look at that. Well, if it's really, really far away, that means, the ring or the point P is really far away from the ring. Then if I come back here, I can say k times x times q over, then I can kind of ignore A. So it becomes x squared to the 3/2. So x squared 3/2 basically just gives me, x cubed. Then this x going to cancel out with that. So it becomes 2. So it becomes k q over x squared, which is again shows that ring going to just behave like a point charge, kq over x squared, kq over r squared, kind of like similar to that, right? That means at this particular, let's say range, right, when x is much, much greater than a, you basically have that. All right, so you can see, right, the calculation for the continuous charge distribution can be really, much, much, complicated compared to the, point charge distribution. And they can be like even more complicated depending on the specific problem. For example, I want to also kind of show you one other, calculation, so that for the, let's say, some kind of rod. And remember, so that example that we looked at before here is you have a rod, one dimensional, right? But you have a rod and you are trying to find the electric field at point P on the same axis. What if the point P of interest is not on the same axis? So I want to show you like an example where, it's not on the same axis. And let's see what will be the calculation for something like that. All right. So let's say this is our horizontal axis. And let's say we have a rod like this. And it has a length L. Now I want to find the electric field some point P right here. Let's say what will be the electric field at the point P. Okay, so what we do here is we draw a line. Okay, try to. All right, I can use this fancy tool. There we go. So let's say this is what I want. I want to find the electric field at this point P. Okay. Now, this is uniformly distributed, rod where the charges are distributed uniformly, where lambda represents that, linear charge density, which remember is Q over L. That means, Q is the total charge, L is the total length. And this rod is a collection of many, many particles. That means what we do, very similar to the previous example. I choose some kind of, element. So that means I choose a small element. And I'm going to say that this small element has a charge dq, right? So it has a charge of dq. Okay. And I'm going to give it a size as like, let's say dx. Let me do dx prime, for example, dx prime. Okay. Because one thing I have here is this. So let's say this is in terms of the right end of the rod, let's say has a distance r from that point P. And if I'm, drawing a line exactly to the middle of the rod, then I can say that, in a way, that the rod has angle theta, right? That means, the right end, it has an angle theta with respect to that point P. But then when I'm doing for my particular element, dx prime, right? So that means that's my small element has a size dx prime and charge dq. Then what I can say is that the distance of that particular charge, or, that element will be this guy over here. And then this will be like r prime. Let's call this r prime. And this theta here, then theta prime. That's for my element. Remember, I'm going to then do everything with respect to my, element chart, right? All right. This guy, dq, then if you look at then the radial direction, right, it's going to give me an electric field in this direction. So this is going to be then dE. This is electric field due to this guy. All right. But one thing I have here is, again, symmetry will allow me to see that if I choose another point, let's say, which has, my first element has an x prime distance from the origin. If I choose another element right here that has, let's say again, dq, let's say dq double prime and dx, let's say dx double prime, which is exactly equal to the dx, right? Dx prime. So if I look at this guy over here, I can see that it also contributes dE. And if I break those down into components, both of them, right, I can see their x components going to cancel out. Again, using the symmetry. Okay. So now what I can do here is I can find the expression dE for the electric field that, let's say, that element generates. This dE is equals to, I can do it in terms of, k, but let me also do it in terms of this 1 over 4 pi epsilon naught. Remember, they are equivalent. So 1 over 4 pi epsilon naught dq over r prime square. This is then the electric field, magnitude of the electric field that it generates. All right, so, but what I'm going to do, I'm going to say the lambda, which is equals to Q over L, also equals to dq over d, you know, let's say dx prime, because the x prime is the the size of my element. That means dq can be replaced with lambda dx prime. Okay, so my equation of dE then can be 1 over 4 pi epsilon naught. Then dq can be replaced with lambda dx prime. And then r prime square can be replaced with r prime square plus, let's call this some distance y, right? Point P here, some distance y from the rod. So it becomes y square. That means this is my dE. All right, so then I can see that this dE can be then broke down into x and y component, where x component will be then dE cosine of theta prime, and then dEy will be then dE sine of theta prime. But then one thing we can see here is if I'm looking at in terms of my x components, right, as I mentioned, if I sum them up, I add all the x components for my entire rod, it's is basically going to go to 0, because for any element here, I have equivalent same distance in the other side that's going to give me contribution in opposite direction, and they're going to cancel out. But this is not, because any element eventually going to give me electric field there's going to be in a positive y direction. All right, so then what I have here is dE, y component of dE, right? dEy equals dE sine of theta prime, and dEy, if I replace dE with this expression here, 1 over 4 pi epsilon naught lambda dx prime over x prime square plus y square. I also need to first, I also need to get what the component is. Actually, let me make one correction. The x component is actually in terms of sine of theta prime, and y component in terms of cosine of theta prime. That's because if I take this y prime, that goes right here, which means my angle is with respect to the y-axis. So it means the y component is cosine and x component is sine. Sorry, I need to make that correction. That means I am dealing with the cosine of theta for the y component of that electric field. But again, cosine of theta is adjacent over hypotenuse, right? So I can replace cosine of theta. So if I'm looking at this theta prime, so then triangle is like this, where this is y and this is x prime. So then cosine of theta prime, right, is going to be adjacent x over, so I'll put like r over here, right? So adjacent, which is y over r. So y over r, where r is the, r prime, right, is the hypotenuse. Well, then becomes y divided by r prime, then it's x prime square plus y square 1/2. So I get that. That means this cosine of theta prime is replaced with y over x prime square plus y square 1/2, which is again kind of similar to the previous example that I did. That means this dEy expression is going to be then 1 over 4 pi epsilon naught lambda dx prime, combining the denominator is going to be x prime square plus y square 3/2. Okay. All right. So then what I do is integrate both sides. The left side is, integral of dEy gives me dEy, or gives me Ey. So this is Ey. The right side, let's first take out the, some of the constants. So 1 over 4 pi epsilon naught is a constant. Lambda is a constant. And if I look at everything else in terms of what else can I remove from the integral, well, there's also, I forgot y over there, right? There's also this y over here, so lambda times y. But then everything else has to stay, because what I have here is then dx prime over x prime square plus y square 3/2 cannot come out. Why? Because for my any element that I'm choosing, x changes, right? For any element, x changes. That means if I'm doing this integral, x, x prime square plus y prime square 3/2 stays inside my integral. That means I have to integrate using that. Now, if I have this, then I have to go in terms of negative L over 2 length to positive L over 2 length, because that means I'm going to go from here to there, integrate from there to here, which is, this is negative L over 2 and this is positive L over 2. That's the limits of my integration. Okay. Excuse me. All right, so this is what we get. Now the question is that how do we evaluate this integral? Because this is, relatively not necessarily complicated, but not a straightforward integral. Well, hopefully this is where then, calculus 2 knowledge comes into play. That means, something like this you should have learned in calc 2. What we do, we say then, all right, so then x prime is equals to y tangent of theta prime. Basically do the trig substitution. X prime equals y tangent of theta prime. Then dx prime over dt d theta prime, let me then take a derivative with respect to theta, then this will give you y secant squared theta prime. Okay, because one thing we're doing the substitution, then we also need to substitute dx prime. So we find what the dx prime is then equivalent to. So dx prime equals then y secant squared theta prime d theta prime. All right, so that's basically what dx prime is. So which means I can come back and say, all right, so it's 1 over 4 pi epsilon naught and lambda times y. And then for the integral, what I do here is dx prime is replaced with y secant squared theta. So secant squared theta prime d theta prime over then x prime square plus y square. Well, now what I'm saying is that x prime is a y tangent of theta, so it becomes y tangent of theta prime square plus y square 3/2. All right, so continue 1 over 4 pi epsilon naught lambda times y. By the way, now all I need to do is also get my limits change, right, with respect to that. That means when x is negative L over 2, what is theta? When x equals plus L over 2, what is theta? So basically, if you look at back over here, where instead of doing negative L over 2 plus L over 2, you can see, right, we're going from here where this is basically negative theta to here where this is theta. That means, if I'm doing that integral, it's going to be negative theta to positive theta. All right, then I have y secant squared theta prime d theta prime. At the bottom, then I'm going to have y squared tangent of theta square and another y square. So then I can factor out y square, right? So let me do this, so y square tangent of theta prime square plus another y square 3/2. So what I can do here, I can factor out, y square. If I factor out y squared, then I get tangent of square theta prime plus 1 3/2. And if you hopefully remember, right, this is equal to then secant squared theta. Okay, that means I have then lambda y over 4 pi epsilon naught, an integral from negative theta to theta, y secant squared theta prime d theta prime over y square. And then in a parenthesis, I get secant squared theta. Then if I take that secant squared theta to the power of 3/2, Well, I get secant cube theta, theta prime, secant cube theta prime. So remember, there was a secant squared theta prime at the top, secant cube theta, prime at the bottom. There's a y over here, y squared over there. So this cancels out, that cancels out. So I end up with 1 over 4 pi epsilon naught from negative theta to theta. So the only thing basically survives at the top is, let's see, d theta prime. By the way, this was like y cubed. Let me make sure that I'm doing it correct. So that's y cubed if I factor out. Then I end up with theta prime, d theta prime, then y square secant theta prime. There you go. So again, this was y cubed. At the top, I had just y. And then this will cancel that and give me y squared. Okay, so this is what I end up. And then what I end up with here is this. 1 over 4 pi epsilon naught from negative theta to theta. See, I have 1 over secant theta. Hopefully remember 1 over secant theta is then equals to cosine of theta. Okay, cosine of theta. But then I have 1 over y squared. 1 over y squared, is just constant. So I can just remove that. Remember, so I already had y lambda times y. So this was lambda times y. And now I take out y squared, this y squared, and which will cancel out with that. And then what I have here is integral of cosine theta prime d theta prime. You can see, right, I just basically simplified my equation into just integral of cosine theta. So, all right, so lambda divided by 4 pi epsilon naught times y. Then I have integral of cosine theta d theta. Okay. So which should just give me, 2 sine of theta when I do that negative theta and theta together. When I cosine theta prime is just sine theta, integral of that. And then when I, go from negative theta to theta, I get 2 sine of theta. That means my final answer finally is 1 over 4 pi epsilon naught 2 lambda sine of theta over y. Okay, that's my final answer. But then what I can do also is just, replace lambda with, whatever it was, right? Remember Q over L and things like that, right? But the idea here is that you get something like this. And you can see, right, how much work we did. Look at all that. That's how much work we did just to find electric field of a one-dimensional, right, distribution for the rod, one-dimensional rod on the x-axis, and we wanted to find the electric field on the y-axis. Remember, so if the electric field was on the same axis as the rod itself, it was a lot more straightforward example. And this one, we have to do all this calculation. Yes, it is very tedious. It is, requires a lot of calculus. But the next part of this, chapter, then we talk about Gauss's law. And the Gauss's law allows us to do this exact same calculation. That means you have a rod like this. I want to find the electric field some point P above the rod. It will take me only 2-3 steps to get the answer. Gauss's law allows us to use this, some concept of electric flux. It allows us to use the symmetry and get same thing with much simpler way. And that's, why we just show you this. And, basically, this is one way to find it, technically using the Coulomb's law. And then there's also Gauss's law, which can get the job done in much simpler way.